All right, now let's look at different types of reactions. We can, in general, break reactions down into a couple of different specific types. And by understanding the specific types, it makes it a little bit easier to balance the reaction and to describe what's going on. So in this video, we're going to look at a couple of those types. One of them are formation reactions, which are also called addition reactions or combination reactions. But I don't remember which term each of the class textbooks use. They may use more than one of those and use them interchangeably. But anyway, those three terms are all interchangeable for formation reactions. We're also going to look at decomposition reactions and combustion reactions. And then, not in this video, but later in the semester, very soon actually, there are a couple of different reactions. I'll just list these here for completion. We'll also be looking at metathesis reactions, acid-base reactions, and redox reactions, but that'll be a little bit later on. All right, so let's go ahead with formation reactions. So addition reactions or formation reactions are those that follow the pattern where we've got two things reacting together, combining to make a third thing. So we can write this as A plus B equals C. And a lot of times A and B are elements, so you can combine element A and element B together to make a compound, which is C. And that's the kind of reaction we've got here that we'll look at in a minute. But A and B don't have to be elements. You could react a compound and an element to make some larger compound. As long as you're combining two things together, adding them together to make a third thing that incorporates both of them, that's an addition reaction or a formation reaction. All right, so for example, let's look at this one. Might be asked to write a chemical equation showing the formation of sodium chloride from its elements. Right? So this is the same reaction that we were looking at in a previous video. So we're talking about the formation of sodium chloride. So we can put that on the right-hand side, and we're forming it from its elements. So that means we're starting with sodium and chlorine. And if it doesn't tell us anything to the contrary, then we should assume these are under standard state conditions. And sodium, we know, is a solid. Chlorine, we know, is a diatomic gas. And sodium chloride, because it's an ionic compound, we know that's going to be a solid. And then we just need to balance this. Since we've got two chlorines here, we're going to need a 2 here. And so to complete the balancing, we'll put a 2 there. And that gives us our completed and balanced formation reaction. Okay, let's take a look at another one. Write a chemical equation showing the formation of nitrogen dioxide gas from gaseous nitrogen monoxide and oxygen. Right. This is an important reaction. This is an important reaction in the formation of smog. Right? And smog is a kind of pollution. People often think of smog as just being just normal pollution, but smog is actually a specific thing that happens when you get the right pollutants in the atmosphere. You get a mixture of nitrogen dioxide and ozone and a couple other things. And the the nitrogen dioxide is kind of an orange-brown color. And this pen actually is a really good approximation of what nitrogen dioxide looks like. And if you're ever in an airplane and you take off from a large city, if you look back at the city, a lot of times you'll see something that looks like this. You'll see just kind of an orangey haze lying over the city. And that orangey haze that you see over the city is smog. And the smog is orange because it includes that nitrogen dioxide compound. And the nitrogen dioxide is formed from nitrogen monoxide, which is a component of automobile exhaust. And so if you get a lot of cars in a large city, that produces a lot of nitrogen monoxide, and then that can react to make the nitrogen dioxide that you see in this smog. Okay, so let's go ahead and look at the reaction. Okay, so we're talking again. This is a formation reaction. Talking about the formation of nitrogen dioxide. So that's going to be our product. Right? Put that over here, and remembering our prefixes and the rules for nomenclature of molecular compounds, we know that's NO2, and it's being formed from nitrogen monoxide and oxygen, right? So that's basically what we start with. Since the oxygen that we're talking about is oxygen in the air, this is normal oxygen under standard states. So this is a diatomic gas. The NO here, it tells us in the reaction that nitrogen monoxide is a gas, and it also tells us that nitrogen dioxide is a gas. So we've got everything in the correct states. We got all the formulas right, and now we just need to balance them, right? So we've got our product over here, NO2, has 2 oxygens. So no matter what we do, we know we have to have an even number of oxygens on both sides, right? And since there's only 1 oxygen over here in NO, we could try putting a 2 there. So they'll get 2 oxygens from the NO, and that one sure we've got an even number of oxygens. So we've got 2 NOs, now we've got 2 nitrogens, we'll have to put a 2 over here. A lot of times balancing these is just a matter of just kind of playing around with them, putting numbers in until you get everything to work out. With the problems that you're asked to balance, sometimes there are tricks. When we get to combustion reactions in particular, I'll show you a trick to balancing it. A lot of times it's just kind of playing around with it, kind of like doing a crossword puzzle or something like that. You just got to keep playing around with coefficients until you find something that works. Okay. Generally speaking, you should be able to balance these with, 2s and 3s and 4s, maybe 5s and 6s. But for most of these, the coefficients are generally going to be pretty small. If you find yourself having to use really, really large numbers like 31 and 17 and crazy stuff like that, you're probably making it too difficult. You probably missed something simple. You might want to go back and look at it. All right, and I guess I'll point out in that also, combustion reactions are a little bit different. Combustion reactions, because some of the molecules are large, you do sometimes get large coefficients in combustion reactions, but those are pretty easy to balance. All right, take a look at some more. Okay, I'm going to give you 2 here to practice on, 2 addition reactions. The first one's actually both these are a little bit tough. I didn't intend to make really tough ones, but these are a little bit challenging. Read through the questions, hit the pause button, see if you can write balanced reactions for these, and then unpause it, and we'll check our results. Okay, the first one is forming rust, so I'm going to use red for this one. And talking about the formation of rust, which it tells us is iron 3 oxide. And remember that what this 3 means here is that the oxidation number, or the charge on the iron, is +3, and the charge on oxygen for an oxide is -2. Right? This goes back to the work we did on nomenclature of ionic compounds. Right? So in order to balance this, we're going to need 2 irons and 3 oxygens. Okay? And we know that rust is a solid because we've seen it, right? And the question asks us to balance this formation reaction from its elements. So the elements in this case would be iron, and again, barring any evidence to the contrary, let's assume that we're going to balance them from their standard states. That's what we would generally do. And now we just need to put in our coefficients. Right? Looks like my plus sign's a little too far over. There we go. And I can see that no matter what we do with our oxygens, on the left we're going to have an even number of oxygens, either 2, 4, 6, 8, 10, something like that. So in order to have an even number of oxygens on the right-hand side, we might try putting a 2 here. And if we put a 2 there, that gives us 6 oxygens on the right. So in order to get 6 oxygens on the left, we can put a 3 here. And then that gives us 4 irons on the right. So if we put a 4 there, we get 4 irons on the left. Okay. And there we go. There's a nicely balanced reaction. Okay. And the second one, let's see, formation of liquid sulfuric acid from sulfur, oxygen, and water. Okay. Sulfuric acid, we talked about nomenclature of acids a while back. And you remember, I hope, that sulfuric acid is H2SO4, and the problem says we're producing it as a liquid, and we're producing this from sulfur, which is a solid, and from oxygen, and from water. Okay. All right. Now, let's see. We've got more oxygens on the left than the right. Well, how about this? It looks like on the right, we're going to have, depending on what coefficient we put here, our number of oxygens is either going to be 4 or 8 or 12, something like that. But it's going to be an even number, right? And right now we have an odd number of oxygens in this water. So I'm going to try putting a 2 here, right? So that we at least have an even number of oxygens on both sides, right? If I put a 2 there, this gives us 4 hydrogens on the left. So in order to get 4 hydrogens on the right, I would need a 2 here, right? And that gives us 2 sulfurs. Put a 2 here. And now if we count up our oxygens, we've got, on the right-hand side, we've got 2 times 4. We've got 8 oxygens on the right. And on the left, we've got 2 oxygens here, which means we need 6 oxygens here. We can get that if we just put a 3 there. Okay. And so this one actually, like I said, this one actually is a little bit tricky. Trickier than I think most of the ones you'd get. Take a look at the study guide. There are several of these. There's some of these in the study guide, and I think those are a good indication of what you can expect in terms of difficulty on these kinds of questions. Okay, so let's look at the second group. These are decomposition reactions. Decomposition reactions are sort of the opposite of formation reactions. These are reactions in which we've got one thing that breaks apart into 2, or it could be more things, right? It could be A plus C plus D. But the idea is you start with one product and that breaks up into smaller parts. And again, the parts over here can be elements. You can have something breaking up into its elements, or it can break up into smaller compounds. Okay, so for example, we could take a look at a chemical reaction for the decomposition of hydrogen peroxide into water and oxygen gas. And hydrogen peroxide spontaneously dissolves or spontaneously decomposes to make oxygen gas, but it decomposes so slowly that you don't notice it. There's a really popular chemical demonstration that been making a lot of people making videos about this that show up on YouTube, called Elephant's Toothpaste. And in Elephant's Toothpaste, what you do is you take a sample of hydrogen peroxide and you add a catalyst, and that catalyst causes this reaction right here to go much, much faster. and it makes the oxygen gas very quickly. And if you add some kind of soap to it, then the oxygen gas that comes out makes a bunch of bubbles, right? And so you get something that looks like that, where it just foams out and rushes out of the flask. If you do this just right, you can get it to shoot 3 or 4 feet up into the air. It's really kind of spectacular. People have been doing this on like the Tonight Show, and there are a bunch of videos online. Anyway, if you're curious, go to YouTube and search for elephants toothpaste, and you'll see a bunch of reactions like this, but they'll be much cooler. You can also put food coloring in there to make them come out different colors. People do all kind of fun stuff. All right, but what we want to look at right now is the reaction. All right, so this is a decomposition reaction. We're starting with one thing, and it's going to break apart into smaller parts. So we start with our hydrogen peroxide, and the hydrogen peroxide is dissolved in water. So put our AQ for aqueous there, and this is going to break apart into water and oxygen gas, right? And so we can look at this and play around with it a little bit. Again, no matter what we put over here, we're going to need an even number of hydrogens and an even number of oxygens on the right. We've got an even number of hydrogens here, but we have an odd number of oxygens. So we could fix that by putting a 2 here. All right, and that gives us 4 hydrogens on the left and 4 oxygens on the left. And so we can balance that whole thing if we just put a 2 here on the left, right? I think I may have just mixed up my left and my right. Apologize for that. But in any case, there's our balanced reaction. Okay. All right, here's another example. This is one, this is something that is done in the concrete and cement industry. They use limestone. Calcium carbonate is called limestone. That's one of the basic ingredients in making cement. And what they do is they take that limestone, and this is a solid. We know it's a solid because this is an ionic compound, and ionic compounds are solids. I'm going to move this over a little bit. And when you heat this up, sometimes chemists put a triangle over the air to indicate heat. If you take calcium carbonate and heat it up, it produces calcium oxide, also an ionic compound, so it's a solid, and CO2. And this is one of the reasons that the construction industry, production of cement in particular, is a really important part of the greenhouse gas problem. There are 2 parts of this. One is that in the process of making cement, calcium carbonate is heated to produce calcium oxide, which is an important component in the process. And it also produces CO2. And so that's part of the greenhouse gas problem. The other thing is just this, that in order to drive this reaction, you have to get very high temperatures. And creating those high temperatures is just very energy intensive. So cement production is very energy intensive and a large contributor to greenhouse gases. All right, so we've got our reaction here. This is our reactant, and it's decomposing into these 2 products. We know that carbon dioxide is a gas because we just know carbon dioxide is a gas, right? And Calcium oxide is a solid because it's an ionic compound. Take a look at the balancing, and in this one, it looks like we got kind of lucky, right? This thing is actually already balanced with ones as the stoichiometric coefficients for all of the species. So this one is already balanced as it is. All right. Okay, let's take a look at two more, and we'll do the same thing we did last time. Take a look at these, hit the pause button, see if you can write decomposition reactions, put in all of your states and balance them, then unpause, and we'll compare our results. All right, so for the first one, we've got decomposition of ammonia. That's one of those compounds that we learned, kind of a special compound. We're talking about molecular compounds. Okay, ammonia is NH3, and it's decomposing into its elements. So that means it's going to break down into nitrogen and hydrogen, and we're going to put everything in their standard states. Nitrogen we know is a diatomic gas, and hydrogen is also a diatomic gas. All right. And now in order to balance this, let's see, we've got two nitrogens over here on the right hand side. We've only got one on the left. So we'll try putting a 2 here. And if we put a 2 over there, that gives us 6 hydrogens on the left. So we need 6 hydrogens on the right, and we can get that by putting a 3 there. Okay. And that one's pretty simple. We got that one all balanced. Okay. All right. Next one, decomposition of carbonic acid, which again we talked about nomenclature of acids in the last semester, so you should know H2CO3, but in case you don't, I gave that to you here. This will be our reactant, and it says that it's aqueous. That means we've got a solution of carbonic acid, and it's breaking down into water and carbon dioxide gas. Water, of course, is a liquid. If the water was not a liquid, probably would have said producing steam or ice or something instead of saying water. If someone says water, generally I think you can assume they mean liquid water. All right, so here's our reactant breaking down into these two products. And if we count up our atoms, we've got 2 hydrogens on the left, 2 hydrogens on the right, 1 carbon on the left, 1 carbon on the right, and 3 oxygens on the left. And on the right hand side, the oxygens are divided between the water and the CO2, but if you count them up, there are 3 on the right, so that means 3 on both sides. So this is balanced as it is without any extra coefficients. All right, lovely. Okay, now let's look at the last one for today, and that is combustion reactions. All right, combustion reactions are those where you combust an organic compound, right? And I'm going to write this in a very general form, right? CXHYOZ, and that just means that this is a, you might see it some of the textbooks say combustion of carbohydrates, and basically that just means any compound that contains carbon and hydrogen and, well, and oxygen, right? And it doesn't really matter what these are. Some of these could even be a 0, right? So this would also be true for something like this if you didn't have any oxygens, just an alkane, a compound with just carbons and hydrogens. Okay. So anytime you do a combustion reaction with an organic molecule, uh, the reactant, in order to do the combustion, it has to react with oxygen. So you've got to have oxygen over here on the reactant side, and that the products are always CO2 and water. And even though combustion reactions may take place at high temperature and initially produce steam, we typically balance these reactions with things in the standard state. So we usually balance them with water as a liquid. Okay. You might come across one that specifically says gas phase water or steam or something like that, and then you can put in the G. But if it doesn't say so, assume that you should balance it with liquid water. Okay. There also may be something in your textbook that takes this general formula and puts something like, I don't even know how this works, x plus z. I don't know what it is, but there's some kind of formula that shows up in some textbooks where they take all of these subscripts and then show how all those subscripts appear over here as stoichiometric coefficients. I wouldn't worry about that because we've got a really simple way to balance these. And trying to memorize all of that, I think it's just not worth your time. Okay. So let's take a look at a simple example. Okay. Let's look at combustion of methane. Okay. So if we're asked to write a reaction or a chemical equation for the combustion of methane, we can start with methane, which is CH4. Because it's a combustion reaction, we know that we have to react it with oxygen gas, and we know that the products are always going to be CO2 gas and water. Okay. All right. Now, balancing these can sometimes be kind of tricky. I think this one's going to be straightforward. We'll talk about the tricky ones later. This one's going to be simple. Okay. We've got one carbon here, so that's fine. We've got 4 hydrogens here. We need 4 hydrogens here, so we'll put a 2 there. And this means that now on the right-hand side, we've got 2 oxygens here, 2 oxygens here. That's a total of 4 oxygens. So in order to get 4 oxygens on the left, we'll put a 2 there. Okay. All right. And that one was pretty simple. Okay. We'll look at a trickier one next. Okay. Let's write a chemical equation showing the combustion of propanol. All right. So this is a 3-carbon chain with hydrogens all around it and an OH group at the end. Okay. So for our combustion reaction, we take the substance that we're interested in, our propanol. In this case, we're told that it's a liquid. Because it's a combustion reaction, we know that the other reactant is going to be oxygen, and we know that the products are going to be carbon dioxide gas and liquid water. All right. So, all right, let's work on balancing this one. We've got 3 carbons here. So go over on the right-hand side, put a 3 there for the carbons. Okay. We could balance our oxygens, right? We've got 1 oxygen here, 2 oxygens here. That's 3. On the right, we've got 6. We've got 7. So we need 7 oxygens. We've got 7 oxygens on the right. We need 7 on the left. So we could put a 3 here. That'll give us 6 oxygens here, 1 here. That's 7. But there's a problem, right? When we set this up, we've balanced everything except for the hydrogens. And so now if I try to balance the hydrogens and come and put some kind of a coefficient here, I will have screwed up the oxygens, right? And if I balance the oxygens by putting a number Here, I'll change the number of carbons. Okay, so the trick to balancing combustion reactions is, let's back up again. There are two tricks. Okay, first one is save the oxygen for last. And the reason for that is you can balance everything else very, very easily, and then figure out how many oxygens you've got on the right-hand side, and then based on that, figure out what coefficient you need there on the left. You can put that in, and you can fix the oxygens without messing up anything else that's already been balanced. Okay, so saving the oxygen for last is always a good idea in combustion reactions. Okay. All right, so let's do that. We can look at our carbons first. We've got 3 carbons here. Oops. We've got 3 carbons here. So we need a 3 there. All right. We've got 8 hydrogens here, right? 7 over here and then 1 more over there. So that's a total of 8 hydrogens. In order to get 8 hydrogens on the right, we need to put a 4 there. Okay. And now, if we look at our oxygens, we have got 6 oxygens here and 4 oxygens here. Is that right? Yeah. So we've got 10 oxygens on the left, and on the right we've got 1 here, and we need to put something over here. Okay. So we need a total of 10 oxygens on the left. We've already got 1, so that means we need 9 oxygens over here. Right? There's no way that we can get 9 oxygens because the number is always going to be it's always going to be an even number because we've got 2 oxygens. So this is where the second trick comes in. When you're balancing combustion reactions and you save the oxygen for last, sometimes you end up needing an odd number of oxygens. In this case, we need to get we need a total of 10, but we need 9 oxygens right here. So the way we're going to do that is we're going to do a little 2-step process. Put in 9 halves here, just as kind of a placeholder, right? And if we have 9 halves of an oxygen molecule, which would be 4.5 oxygen molecules, then this would be a total of 9 oxygens. And then if we add that oxygen, that gives us 10. So that'll be our proper balancing. And there are some instances where you want to balance things with fractions, but we'll talk about those later. Generally speaking, we want to balance things with integer numbers, so we don't want to do fractions like this. That's considered incorrect. It's not super incorrect, but it's not quite what we want. So in order to get rid of that fraction, then what we'll do is we'll just take this whole equation and multiply it by 2. And when we do that, we get 2 propanols and then 9 oxygens. Reacting to give us 6 CO2 molecules and 8 waters. Okay. And we might double check. Carbons, we've got 6 carbons on the left hand side, and we've got 6 carbons on the right hand side. Hydrogens, we've got, let's see, there are 8 here in this propanol molecule. We've got 2 molecules, so that's 16 hydrogens. And over here, we've got 2 hydrogens in each water molecule. We've got 8 of them, so that's 16. That's good. And then for our oxygens, we've got 2 oxygens over here and 18 oxygens over here, so that's 20. And on the right hand side, we've got 12 oxygens here and 8 oxygens here, so that's also 20. Okay. It helps particularly with complicated complicated equation balancing, sometimes it's nice to write all the atoms down, keep a tally of what you have on the left and what you have on the right. Anyway, so that's good. We got that one balanced. Lovely. And now I'm going to give you a couple of combustion reactions to balance on your own. All right. So as before, hit the pause button, work through these, see if you can get them balanced, and then unpause and we can look at our results together. All right. So for the first one, we've got methanol. And of course, it's going to be reacting with oxygen. Make CO2 and water. Okay. I've got 4 hydrogens on the left, so I'm going to put a 2 there to get 4 hydrogens on the right. I've got 1 carbon on the left, 1 carbon on the right. That all looks good. Now on the right, I've got 4 oxygens, right? On the left, I've got 1 here and 2 here, so that doesn't work, right? I need, this needs to be 3 oxygens in order to work out, so that would have to be 3 halves. Right? And now I'll just multiply the whole thing by 2. That gives me 2 carbons on each side. It gives me 8 hydrogens on both sides, and looks like 8 oxygens on both sides. Wonderful. Okay. And now here's one we've got. We've got a big number here for hexane. We've got 6 carbons. So this is an example of where the some of the stoichiometric coefficients might start to get a little bit large. Okay, but since we have a systematic way of doing this, that's not going to be a problem for us. All right. So we'll start with our hexane. C6H14. React that with oxygen gas to make CO2 and water. I've got 6 carbons on the left, so I'm going to put a 6 here, so I have 6 carbons on the right. We've got 14 hydrogens on the left. So in order to get 14 hydrogens over here, I need a 7. Okay. And now if we count up our oxygens, we have 12 oxygens here and 7 oxygens here. So that's a total of 19 oxygens. Right. So if this needs to be 19 oxygens, and it's a diatomic molecule, the only way I can get that is if I use fraction 19 over 2. And again, since that's a non-standard way of balancing this, we'll multiply the whole thing by 2. So I'll have 2 hexane molecules plus 19 oxygens gives us 12 CO2s and 14 waters. All right. Lovely. Okay. All right, so what we looked at today, we basically looked at 3 kinds of reactions, right? Addition reactions, also combination reactions or formation reactions, whichever term you want to use, decomposition reactions, and combustion reactions. And on the combustion reactions, It's important to remember, first of all, that you're reacting with oxygen and the products are always CO2 and water. And the other thing is there are two tricks to these. One is balance the oxygen last, and when you balance the oxygen last, sometimes you get a fraction, right? Like we just had 9 halves or 17 halves or something like that. Go ahead and balance it with the fraction, but then after you've balanced it with the fraction, multiply the whole reaction by 2 to get rid of that fraction in the balanced equation. All right, terrific. That's it for types of reactions. Work on those and work through the study guide, and then we'll be back with another video.